IDEKO is a Spanish research center specialized in industrial production and manufacturing technologies, with the aim of promoting technological innovation on its customers. Precision engineering is among our demonstrated technological expertise, with an excellence bet at research and development of precise machine-integrated vision technologies. For IDEKO, the ZAero project is an opportunity to increase our expertise in precise machine vision technology, contributing to a driving sector such as aeronautics for topmost quality assurance and inspection technologies in manufacturing of carbon fiber components. Besides being responsible for the exploitation and dissemination work package, IDEKO focuses its main activity in the ZAero project on the development of novel calibration means for machine-integrated vision sensors for monitoring dry carbon fiber layup processes. For the automated dry material placement process, two complementary machine-integrated digital camera systems are developed in the project. First, laser triangulator sensors for measuring height variations during the dry material placement process, and second, photometric stereo sensors for in-machine measuring of fiber orientation. As for every measuring instrument in industrial metrology, in this case, both sensor approaches share a common nature. A machine-integrated set of multiple digital cameras must be accurately calibrated to get precise and reliable in-machine inspection data. In the ZAero project, topmost inspection performance is pursued for monitoring the automated layup process, aiming at a measuring uncertainty ranging 0.1 millimeters for height measurements by laser triangulation and 0.1 degree in fiber angle orientations by photometric stereo. Correspondingly, custom-made calibration solutions must be developed for the set of machine-integrated cameras so that such accuracy requirements are fulfilled. In vision-based measuring systems, calibrating a set of cameras means determining their corresponding extrinsic and intrinsic parameters. The extrinsic parameters describe the pose and relative orientation of each camera in the frame at which each measuring results might be expressed, for example, the machine frame. On the other hand, the intrinsic parameters from the set of optical characteristics such as the focal length and the correction parameters needed to compensate for optical lens distortions. As a result, two complementary calibration approaches have been designed and implemented in the project. First, an in-machine, fully automated and easy-to-use calibration solution was developed. A commercial flat calibration artifact is placed on a predefined position at the machine frame, and several images are taken on it by the cameras from different controlled CNC positions. Images are processed and calibration parameters are determined in process. The solution demonstrates to be cost-effective and precise enough for ensuring an accurate performance of most of the intended in-machine measures. A second calibration prototype was developed with the aim of increasing calibration accuracy, but also keeping a fully automated and in-machine approach. In this case, a machine-integrated mechatronic solution was developed, enabling the in-process creation of custom-designed optimized 3D calibration object for increasing calibration accuracy other than limiting the performance to the use of flat commercial calibration artifacts. Additionally, high-precision calibration spheres were used for optimal image quality. A still cost-effective but precise solution was demonstrated based on a relatively cheap mechatronic with 3 controlled but inaccurate axes, ranging at 0.1 millimeters, along with a custom-designed multi-camera system for precise 6D tracking of the calibration object, ranging at 0.01 millimeters accuracy. In the future, further work will be done for increasing the volumetric accuracy of the multi-camera 6D tracker, aiming at breaking the barrier of 0.01 millimeters 6D tracking accuracy towards performing closer to just a few microns.